All right, today's class is our review period. So for the next 50 minutes, I will just be fielding questions from all of you and doing my best to help you understand those concepts. So this is the one class period per exam where you come prepared with content and I do not. So questions?
Is there one bullet point on the study guide where it's saying I will struggling to define this?
Yeah.
What's an abstract data type?
Abstract
What programming construct it uses?
Let's talk about that. That is a very good point. Yeah, I am currently recording, so I will get that up as well so that people can refer back to it at a later date as well. So an abstract data type is something that tells us how to do something, or it tells you what you can do, but not exactly how it is done underneath the hood. So the abstract data type that we have all studied so far is list. It's not array list, that is a type of list. It is not linked list, that is also a type of list. So the abstract data type is abstract and has many implementations. So we've seen an array list implementation of a list. We've seen a singly linked list implementation of a list. We've seen a doubly linked list. We've seen a circular doubly linked list. All of these are implementations of the list abstract data type. And what I mean by this is from the client's perspective, they can make one of these and it looks almost exactly the same to use any of these objects. So for instance, you could type array list integer list 1 equals new array list. Man, Java is a long, verbose language. So there's one list. We could make a singly linked list of type integer list 2 equals, and at this point, new singly linked list of type integer, etc. And now we have two lists, list 1 and list 2. The difference between using this from the client's perspective is one, they all share the same methods. You can add at the end of any list type. So you can say something like list 1 dot add 4, list 2 dot add 7. These calls look precisely the same. From the end user's perspective, it looks like you're just using a list. But now you all have the experience necessary to know what's going on underneath the hood when we add 4 to an array list is very different from what happens underneath the hood when we add 7 to a singly linked list. But from the client's perspective, they don't know this. It's like driving 2 different cars, or talking to 2 different people, or they're vastly different objects, but they all do the same things. So what object-oriented construct allows us to do this? To define a concept that gets implemented in a bunch of different ways, but has the same name. It is polymorphism, but what did we make the list? It's an interface. So the list interface defines all of the methods that are associated with the list abstract data type. And it tells us that in order to have a list that is going to be used by anybody or is polymorphically allowed to be kind of swapped out, then we need to implement everything that this interface describes. So we need an add method. Would you use a list that did not have an add? If I had a singly unlinked list that couldn't add, then there's no reason to use it because it doesn't have that same functionality. And then we don't get the power of polymorphism where we could make an array list and a singly linked list that have the same information, and we could swap them around depending on our needs. So that is a great question, but that is what we have studied so far. We will see as we continue down the rabbit hole of this course that we are going to be looking at many more abstract data types that have many different implementations, and we're going to be studying more at the interface level than we will at the implementation level. And maybe we'll look at one kind of implementation for this, but we'll see that you can implement this same abstract data type in a bunch of different ways. They use a bunch of different structures underneath the hood to represent the same computation. And the structures underneath the hood are going to have some different pros and cons, or strengths and weaknesses to them. As we saw, if we're trying to compare an array list to a linked list, we found that we would want to use one sometimes and another some other times, depending on how frequently we were calling some of these methods defined in the interface.
You talk about like the restrictions of the iterator.
Yeah, so that is another great point. So iterators, let's start with just the purpose of an iterator. What is an iterator for? Why do we care to implement them?
Modify the list while you're.
Yeah, because we want to be able to modify while we are iterating. That seems like it might be something that is useful. For each student, ask if they have a question. If they don't have a question, ask them to leave. Kidding. But that would modify the list while we are iterating over it. Something, I don't know, that's terrible. Anyone need anything else from the board before I erase and start talking about iterators?
You just turn on those lights and.
Yeah, I guess that is, I think this room does have batteries. The other room doesn't have batteries. Right, that. I made that brighter. There we go. Is that better?
Yeah. And
And it looks okay remotely as well, I think. Okay. All good? All right. Iterators. So we want to modify a list while we are iterating through it. Normally, we can't do this. We get what's called a concurrent modification exception as we try to do this because, well, we are trying to modify something and trying to keep track of what is the current index of what we are focusing on that will be switching around on the fly if we're trying to add or remove. So we need additional logic to be able to handle that, which is the purpose of what the iterator is going to be doing for us. But we can't do things like remove right after we have removed. Why do we think that is?
That's one before you try to move again.
Yeah. Yeah, we have a current element that points to a position in the list. And if we remove, we're getting rid of the current element. If we remove, we don't have a way, we're not setting it to the next element yet, because that's outside of the scope of what an iterator can do, and it requires a bunch of extra work to be able to do that. So an iterator, rather than keeping track of an index, is only keeping track of a current position, or a current node, or a current something. So we have an iterator that's keeping track of, I'll draw this like a linked list. So we start out with current pointing at nothing. And so what methods do iterators have?
As next, next.
As next, next, and we can also implement an add or remove. Yeah. So has next just tells us, is there another node to go point current to? Next says, actually go point it at that node. And then add allows us to add a node after that node, and then remove says we can remove the node that is currently being pointed to. So if we remove what current is currently pointing to, we remove this and we get rid of it. What is currently pointing to? So if we try to remove and then remove again, what do we expect? Some kind of exception. Yeah, some kind of middle pointer exception. We got rid of what it was pointing to, and then we said, get rid of what you're pointing to. We can't do that twice in a row. So the restriction is that we have to call next to actually have current point at the next node before we can do anything like add or remove. So current has to be pointing to an actual node in order to be able to add or remove. That is the important iterator restriction.
You said that it was bringing the, I guess, theta as big O.
Yeah. Yeah, we have three big things we have covered. We've covered theta, we've covered O, and we've covered some second grade version of omega. That was difficult for me, and it still looks like trash. So we have theta, O, and omega. So we use big theta whenever we know for sure the exact order that something is going to run in. 100%, it will not run. There's no reason that it would run in a higher order and no reason that it would run in a lower order. So all of these are asymptotic notations. We can all say theta of n or theta of n squared, O of n squared. I'm just going to leave this as O because it looks weird with an H. We can say omega of n squared or omega of n, and all of those mean the same asymptotic notation. The same functions mean the same thing, but the actual interpretation of what those mean differ. So if we have an algorithm or a method, something that runs in theta of n, let's say n squared, why not? Then we have some reason to believe, well, in fact, we can show, this is proof, that there's no way this runs in any order that is lower than n squared, and no way that it runs in any order that is above n squared. It always runs in exactly n squared. So mathematically, I like to think of the theta as just an equals. For asymptotic notation, it says this equals this, how do I say it? The process through this algorithm equals n squared. Big O says we have an upper bound. So O of n squared, I like to pair with the terminology upper bound, which says that it may run in n squared, and it may run in an order that is less than n squared. But there is no way, for no possible input, will it run in more than n squared time. It may run in a constant times n squared, but that is still order n squared, but it won't run in n squared log n, or cubic, or quartic, or exponential. Anything that is above n squared, it will not run in that order. Similarly, omega is a lower bound. So if we have something like this, omega of n squared, it will tell us that it will run in greater than or equal to n squared. So we pair omega with the best case analysis, O with the worst case analysis, and theta is the best case and the worst case run in the same order. So everything between the best case and the worst case has to also run in that same order. So for instance, we saw that selection sort always ran in n squared. The best case was n squared, the worst case was n squared. So selection sort runs in theta of n squared. No matter how you permute the array, it's going to take an amount of time proportional to the square of the size of the input for selection sort to sort an array. Even if you pass it in perfectly sorted order, it's still going to take time proportional to the square of the length of the array. On the other hand, we saw that insertion sort had a best case that was linear. So if we wanted to talk about the behavior of insertion sort, we could say that we have an upper bound of n squared, but it may run in a better order than that if the input is perfectly sorted. We have no reason to expect that it's perfectly sorted, but when we report the running time of insertion sort, we want to use big O of n squared because it is possible to arrange the input in such a way that it runs in a lower order. We haven't really talked about an example of something that's reasonable with omega, and this is typical in computer science. We don't usually consider the best case too much, but it would say that we've identified a lower bound, that the algorithm won't run faster than this. This is mostly useful in proofs to say something like, I can put a lower bound on this algorithm as exponential, so we just straight up shouldn't use it. It's never going to be useful. Does that make sense?
Yeah.
Any further clarification I can give? I think that it really helps to pair it to some kind of math symbol that you've seen before to help understand exactly what this is. And algorithms will actually introduce you to a couple more of these. I talked about little o and little omega that represent strictly less than and strictly greater than, but we're not going to run into those at all in this class. So know that they exist. I'm never going to test you.
You say in the study guide, we implementing methods for lists.
Yes.
Are you talking about like, so if we wanted to do like a sort or something, is that kind of like what you mean?
Sorting is not technically part of the exam. I'm not having you study for sorts, but that would be something that might be, I would want to add the functionality to a linked list in some way, shape, or form. So that would be some kind of added functionality. I wouldn't give it to you because it's something that I would like to throw a question on a future exam about, not necessarily applied to linked lists, but something that involves sorting. But something that uses logic that you have seen before. So anything, any way that I could add functionality to a linked list that would involve things like loops. You've seen those before. Anything from a prior class. How do you manipulate the aspects of a linked list? You may need to modify where the head or the tail is. You may need to, it's like very similar to the add all from the homework. So that's a functionality that's not part of the linked list, the actual built-in linked list interface. But I could ask you to do something similar to that, that says, here's something we might want to do to a linked list. And it will not involve any new logic that you haven't seen before, but it may be a method that you haven't seen before. It'll use logic that you have seen before. You'll need to show that you can manipulate a linked list. You know what the nodes are constructed out of. You know how to manipulate how nodes are connected to other nodes in order to accomplish some kind of logical task. Yeah. Yeah, we can draw this out. All right, so we have a singly linked list that uses a singly linked node. So a singly linked node is going to have two components. It has a data and it has a next that's going to point to some other node. It may point to nothing, but that is a singly linked list using a singly linked node. And now we construct a list out of these. So we're going to have some number of nodes that connect to each other. The first one we call the head, and the last one we call the tail. And this, of course, points to nothing. So that is a singly linked list. A doubly linked list uses a doubly linked node that looks very similar, it just has three components. We have a data in the middle. We have a prior pointer and a next pointer, or a previous and a next. Now, if we want to make a list out of doubly linked nodes. This points here, this points here, this points here, this points here, this points to nothing, and this points to nothing. We have a head. We have a tail. A circular doubly linked list is again going to use the doubly linked node. Nothing changes about the internal structure of a node used for a circular doubly linked list.
Will you always clarify circular as doubly instead of circular singular?
Yeah, yeah. Because there is also a circular singly. Anytime in this class, I figure if you want the power of a circular linked list, you probably want a circular doubly linked list. I probably won't ask you for any reason about anything related to a circular singly linked list, but they do exist. They are useful. So a circular doubly linked list looks exactly like the doubly linked list. A couple modifications. So we have pointer, 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 but now the previous pointer, the next pointer, now connect the head and the tail.
The computational complexity on the setting here, what's the difference between A and C? If you gave that up, it's, you don't have to give a program or method to a mathematical function. Operations taking solid problem based on the input size, and C is given a mathematical function to be able to report complexity. So there's one like.
Yeah, they're kind of reverse order from each other. So if I give you, it could be something similar to problem 3 on the homework where I say, here's a complexity order. Give me a piece of code that adheres to that, or the other way around, where I give you a piece of code and say, so one of them is directly a specific mathematical function that includes all of the lower order. And then one of those also said that you only care about the order. So I may give you a code snippet and say, similar to problem 2 on the second homework, what is the asymptotic behavior of this function? And the other would be analyze each line, how many times does each line run, use that to come up with a full mathematical function that describes its runtime behavior. More similar to the in-class examples. So all of those are legal types of questions that I could ask you on the exam.
What about non-polynomials for complexity order? I think there was one on the homework that was worse than the.
In question 1, yeah, there were definitely a couple of them that were worse than polynomial. But are you saying like in code form, how do those arise?
I mean, I like Googled it and they were like, this is the worst one, you know?
Yeah, anything beyond polynomials is just not computationally feasible for reasonably large values of the input size. But how they appear in code is, so if you're looking for something that's exponential, it's the exact opposite of something that is logarithmic. So when we were coming up with, when we saw the homework problem that said every pass through a loop, we are having the size of the input. Think of it the exact inverse from that. So now we want to do something like, an example of this would be cracking a password. Writing a program to crack a password. We now need to check every combination, or in fact, in this case, the permutation of every possible value that a password could be. So we need to, in order to be able to solve all passwords of length 1, we need to go through every possible character. So let's say that passwords can only contain lowercase letters, uppercase letters, and numbers. How many total possible symbols are there? Twenty-six, and 10? 62? So all passwords of length 1 are, we have 62 things we need to check. How many things we need to check for all passwords of length 2? And it's not double, multiply, 62 times 62. Because you could have lowercase a followed by literally any character, that's all of these. We could have lowercase b, that is all of these, lowercase c, that is all of these. This continues, there are 62 possibilities for the first character, and for each one of those, there are 62 possibilities for the second character. How many passwords are there of length 3 that we need to check? 62 times 62 times 62? How many of length 4? If we wanted to check all of these, what do we need to do? Add them all together, check all of them with length 1, and then all of them with length 2, and then all of them with length 3. That's a sequential logic. So these would be loops that are after each other. So we add them instead of multiply them. This looks disgusting, and I've only gone up through passwords of length 4. Who uses a password of length 4 for anything? No one will even let you. Has anyone gone to how secure is my password or know of that site? Go there. They don't store your password, you just type it out and it tells you how long it would take the computer to crack it. Because we know that computers can do things like 1 billion times a second. So even this sum is not 1 billion, so this would be cracked very instantly. But type in a password of yours and see how long it would actually take the computer to do this.
400 years.
This is why we use a password system that is exponential in nature. You make a password and it's exponential complexity to crack it, which is why we use them. If we don't want a computer to be able to do something, we need to use something that is exponential in nature.
Password is 500 quadrillion years.
Yeah, that's about how long mine is.
Yeah.
Yeah, so something like 500 quadrillion years. How long does the Earth have left before it is scorched by the sun becoming a red giant? The answer is some number of a few billion years. So if we set a supercomputer, in fact, if we hooked all supercomputers in the world up together and tried to just brute force your password, it would take longer than the Earth has left to do so. That makes you feel pretty secure about your password until it's stored in plain text and leaked by some site that stores it.
Could we maybe just walk through like a function, trying to get them on time,
Yeah,
right? Like just an example.
so we have two different options. We want to just get an order or do we want to get a mathematical function?
I want mathematics.
So I don't have anything more prepared than what was on our slides, but we could go over or through any of the functions that we have written for any of the classes that we are in, and that might help a little bit. Oh. That's why you turn your computer on before you come to class.
Could we do one that's logarithmic in nature?
Yeah,
Explain why it's logarithmic.
Yeah.
Cannot get that for some reason.
yeah. So logarithmic, the idea behind logarithmic is we're each pass through a loop, we are going to be creating a smaller problem, and not just a constant size smaller, but a proportionally smaller problem. So an example of this is homework 2's binary search. We will actually see lots of examples of that in this class. So I'm hoping that even if that is something that you are currently struggling with, this is something that we will see a lot this quarter, because logarithmic is very efficient, and everything that we care about as computer scientists is finding efficiency. So we can either bring up, and I can go over the homework, or I can try to find some other, we'll see plenty of other examples of it. But the idea of the binary search, what that code was doing is we have some haystack. We have some long array. In fact, I probably would draw it even longer than this so that I can showcase exactly what's happening. The first thing it asked you to do was check the middle element. So we identified the middle element as the index of the first element plus the index of the last element divided by 2. That gives us the middle element. There was an offset by 1 in there, so this is the middle element. We check the middle element to determine, is this what we are looking for, yes or no? We know that the haystack is sorted. We've gone through some kind of either insertion sort, selection sort, some sort that is significantly more efficient than that we will look at later this quarter. And we can determine, we know that everything on this side is less than m and everything on this is greater than m. So we can now, with one comparison, determine whether the query is on the left side of this or on the right side of this. In one pass through the loop, we identified which half of this array structure our target, our query is in, if it's there at all. Let's say we discover that it is less than m. This has told us that we no longer need to consider anything from this entire half of the haystack. We've cut the size of the haystack in half with a single pass through the loop. So now we pass in this as L, this as R, and now we find the new middle. We can query, is the middle what we are looking for? If it is, great, we found it. And now what is on the left-hand side of this is less than the middle. What's on the right-hand side of this is greater than the middle. So again, with one pass through the loop, we have the size of the half of the haystack from before. So after 2 passes through the loop, we've taken, maybe there are some power to 1024 elements in this array. And we break this down now, after 2 passes, we're looking at 1/4 of that. What is 1/4 of 1024? 256. So maybe it's in the greater than m this time. So it's in one of these 256 positions, somewhere in this part of the haystack. With one more pass through the loop, we'd be at 1/8 or 128. So we would go from 1024 down to 512, down to 256, down to 128, down to 64, down to 32, down to 16, down to 8, 4, 2, 1. In 10 passes through this loop, we would have identified whether the query is in the haystack or not. And if we did find it, we know exactly where it was. It's either here or it's not in. 10 passes through the loop. Let's say we had 1,000,000 elements in our array. How many passes through the loop would it take? The answer is 20. If we have this 1,000 here, we can basically multiply 1,024 by 1,024. And that's how large of an array we can find with an additional 10 steps. This is the new one as we blow this up to 1,024. So we have 1,024 times this. So that's more than 1,000,000. If we wanted to find a needle in a haystack of size 1 billion, how many comparisons, how many passes through the loop would we need? 30. 1 trillion. 40. It's scary to think that if the needle was a single person on the planet Earth, it would take about 33 comparisons to identify exactly that person. If we could eliminate half the population per query. If the answer, so for the game 20 questions, where you get 20 questions, you can eliminate half of the possible answers with each guess. You can guess something where the size of the problem is 1,000,000 things with 100% accuracy. If you can always eliminate it half the time. So exponential, the exact inverse of exponential is logarithmic. And we find that in computer science, we frequently see logarithmic complexities. The reason that we see them is we have a comparison if else, or greater than less than. And we're able to do something like binary search if we have some way of mapping whatever problem we want onto something that looks kind of like this. And we have structures for storing this as well. So binary search works on an array. Later on this quarter, we will see tree structures where we have a node that splits into 2 children, a left child and a right child. And we just do this over and over. As we do this, we will find that we can easily do this recursively, which is why we are studying recursion, because this is always the same problem. Do I go to the left child or do I go to the right child? All right, do I go to the left child or do I go to the right child? All right, do I go to the left child or do I go to the right child? It's the same question every time. And we will find that the number of nodes that are on each level of this tree doubles, 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 with one more question, which has us going down one more path in this tree, we can answer or find the answer to a problem that is twice as big. Because we can store twice as many things. So for instance, the example that I've been using in office hours is let's play a game. I'm thinking of a number between 1 and 15. If I order all of the numbers from 1 to 15 in what we're going to call depth first search order, we'll study that later this quarter as well, we end up with numbers that look like this. This isn't particularly visible. But this solves the game for us to do it. This tells us what number to guess each pass. So I'm thinking of a number between 1 and 15. On guess 1, you guess 8. And now you either know, yes, the number was 8, or I tell you it's less than that or it's greater than that. This is an example of binary search. If I tell you it is less than 8, we don't need to consider the entire right subtree here. Gone. Not part of our consideration anymore. Now we have this structure. We know that the number that is to be guessed is somewhere in this structure. So we guess 4 as our second guess. Maybe you are told it is greater than 4 and not exactly 4. So now we only have this little subtree to consider. It's either 5 or 6 or 7. We've identified that from just 2 guesses. Maybe you're told it's greater than 6. So you guess now 7 and you have to be right. If it's less than 8, greater than 4, greater than 6, it must be 7. So in 4 guesses, you can for sure guess a number between 1 and 15. And again, this scales in exactly the same way. So that if I were asking you to guess a number between 1 and 1,000,000, you could do so in 20 guesses. Guaranteed. No way you couldn't possibly identify the correct number. Yeah. It's the power of exponential scaling, or the power of logarithmic scaling if you're the one doing the guessing. But you can see the difference here between the number of nodes in the tree structure and the associated number here. We've handled one node here, which is 2 to the first minus 1. Between this, within 2 guesses, we've handled 2 squared minus 1 total numbers. Here we have 2 to the third minus 1. 1, 2, 3, 4, 5, 6, 7. That's 8 minus 1. And then 15 is 16 minus 1. That's 2 to the fourth minus 1. This continues scaling for every possible guess. You just raise the power by 1, raise the power by 1, raise the power by 1. So it's super cool.
You might have sort of already touched on this, but what object-oriented programming construct does the abstract data type use?
Yeah, it's an interface. And the
Okay.
reason it's an interface is because we specify the exact functionality that all lists should be able to give us. And then we define how does one add to an array list? That's an array list question. How does one add to a linked list? That's a linked list question. But all lists must be able to add in order to be an abstract data type list. So an array list is an implementation of the ADT list. A linked list is an implementation of the ADT list. And by ADT, I just mean abstract data type.
When you say be able to draw images, you mean just like be able to draw a building node and like.
Yeah. Yeah, I may ask you to show your work for something by drawing that out. And that may also help, even if I don't ask you something like that, if you have an image and show your work via an image, it's very easy for either the TA or me to see your logic. And I can use that logic to give you partial credit. Wherever possible, show your work. Both of us are looking for ways and reasons to give you partial credit. If you just report an answer, it's either right or it's wrong. The more work you give us, the more work we can see. We can actually look at your process and award you points for the process that you've gone through. That said, if you arrive at the right answer and show work that is wrong and just happen upon the right answer, then we will identify that and mark you down for an incorrect process. So there's a little bit of give and take there, but in general, it's much better to show your work. More people arrive at a wrong answer by using right logic than arrive at a right answer using wrong logic.
What is an abstract data? Because I'm trying, I think I get it because it's like the idea of an interface and the interface of the implementation.
Yeah.
List.
The way that I like to describe it in 212 is something like, if I asked everybody to draw a car, or sorry, not even a car, let's say automobile. Do we think that everyone would draw something that looked precisely the same? No, it's because it's an abstract concept. A motorcycle is an automobile. A truck is an automobile. A helicopter is probably technically some kind of automobile. I don't know, maybe not. Maybe someone thinks it is. But there's a big difference between this generic concept. So an abstract data type says all lists can do the same thing, but the implementations of those lists can be very different. If I asked everybody in here, draw a list, someone might draw an array list, someone might draw a linked list, they'd both be right. It is a list. So they have the same functionality, but the underlying way that they do those things is different. Just like all automobiles can drive, but the way that they drive is slightly different. So the implementations of that are different. And an interface does not specify any implementation. It only gives us a list of methods.
So
And
this
says,
is an ADT and an interface, it's like super close.
yeah, they're very tight knit. It's basically a conceptual idea of a list. We want to be able to store something in an order that has an associated index with its position in that list. All list implementations adhere to that, but the underlying representations can be vastly different, which leads to different pros and cons if you want to remove from a list. What is the associated complexity of removing between an array list and a linked list? They're different. Other questions?
When you say mail common function words, are you talking about like factorial and like?
Yeah, like the ones from homework too. I won't throw any that are crazier than the ones in homework too, but kind of know those associated orders. You should be, if you haven't already, receiving feedback on that homework this morning. Yeah. So if you have any questions about that, the TA is sticking around for a while. I'll have office hours for an hour after class. Feel free to come talk to me for about any confusions you had about those associated orders, and I can try to help clarify that for you. Kind of. So an abstract class allows some implementation. And the reason we want some implementation is if multiple different subclasses have the exact same functionality. So we have something like, what is something that all cars do the same way?
Grocery.
So we could have, you know, maybe we have a, let's try to make this as different as possible, Honda and a Lexus. Two different kinds of car, but if we wanted to write the drive straight method, a Honda drives straight the same way that a Lexus does. So an abstract class would allow us to implement all of the logic for drive straight. All of this would be implemented here, so that we don't have to copy and paste it between these two objects. And now when we make a Honda object, and tell that Honda object to drive straight, it's going to use this code. When we make a Lexus object and ask a Lexus to drive straight, it's going to use exactly the same code. They use the same code to do it so that we don't have to duplicate that code in each of these different classes. An interface allows no implementation whatsoever, so we are not allowed to apply logic to anything, which is necessary because in the list abstract data type, we don't want there to be any implementation. There's going to be some future list that nobody has invented yet that we don't want to force them to use any existing code. We want to give them the freedom to implement it however makes sense to them. So all we do is specify a list needs to be able to add at the end. A list needs to be able to remove at a particular index. A list needs to be able to return the size of that list. All of this is functionality that is common between all lists, but we don't specify any of how it is to be done. And in Java, there's the extra restriction that we can implement any number of interfaces in a class, but we can only extend one abstract class. So when you have the choice between the two, think, are there other things that would make more sense to extend than this one thing? If you're only saving yourself one method of implementation, maybe you want to extend something that saves you 4 methods of implementation instead, because you only get to pick one. In other languages, you get multiple inheritance and you can extend multiple classes, but it creates what we call the diamond of death, which is something that people don't really want to think about. So Java just straight up doesn't allow you to. But if you're in a language like C++, it's a nightmare you can find yourself living. It is very appropriately named. It is the diamond of death. I'll talk more about that in 212 for those of you who are curious. And we're in office hours. It's kind of outside of the scope of data structures, but if you're curious, I'd be happy to talk about it. Last 1-minute question.
It's on the exam itself, I'm guessing it's gonna be mainly be short.
Yeah. Short answer, be ready to write some code. There will be some code implementation.
What would be like an example, like just describing something or implementing what we are understanding of a concept?
I can tell you right now, you'll be implementing at least one new linked list method. All right, excellent job coming prepared with questions. We used the whole time period. There was no awkward staring. Approved. I have office hours now for anyone who has any individual questions about grading, about homeworks, about exam preparation. Let me know how I can be useful.
Sorry.